Hello, so yes, a couple of days ago, well, about 4 days ago, I did this video, which was a response to the Potter's Clay's eclipse video, and I just went through the points that he got wrong, which is that he misunderstood that the place where the place where the moon casts a shadow on the Earth is not the place where the moon is directly overhead on Earth, which is where we say the moon is. Where the moon is moves from east to west, and where the shadow is cast moves from west to east. He got confused about that. So if you're not sure what I'm talking about, you can go back and watch that video. Now, flat earthers have been trying to make some sort of response to this, and one guy in particular, called The Bloody Truth, made a response directly to me, and we can just listen to a little bit of what he says.
Oh yes, let's go through the main points again, you condescending egomaniac.
That's me.
You're saying that the moon's shadow moves faster across the globe than the globe spins. Yet you agree we are discussing the currently accepted scientific, and I quote, standard model of our globe reality.
I think he's quoting me there when I actually said that this was the standard model.
Well, here it is.
To an extent.
So, here we have it, folks. The standard solar model in all its glory. Unfortunately, your standard model has a huge gaping hole in it. Okay, when all the calculations are entered and the graphics are rendered and played at speed, a solar eclipse lasts 4 days.
Right, so he's using this animation to figure out how long it would take the moon to transverse the path between the Earth and the Sun. Unfortunately, this animation is not to scale, not even close. In reality, the distance from the Earth to the moon is about 30 times the diameter of the Earth. So this is nowhere near to scale, and that's a major problem. That's a major part of why he's misunderstood what's going on, and why this video response is just absolute nonsense. One of the great fools of YouTube, deep inside the rabbit hole, he does the same thing. We witness a total solar eclipse becoming a 4-day event, so other flat earthers are getting in on this absolute nonsense. The Potter's Clay himself made a response, not to me, but presumably to Sly Sparking. He shows this ridiculously unrepresentative video where the moon's like somewhere just above the surface of the Earth. Absolutely ridiculous. Now, the other problem that they're having is understanding why the moon casts a small shadow on the Earth, and why isn't the shadow it casts the same size as the moon? Okay, so fair enough. So there's two main points that they're bleating on about. One is that they think the moon should take much longer to transverse across the path between the Sun and the Earth. And they also think that the shadow cast by the moon should be about the same size as the moon. Okay, so what's the problem? Well, in the video I made, I said something that wasn't entirely true. Okay, I hold my hands up. I said that the light from the Sun is parallel. It's almost parallel. It varies by about 0.5 of a degree. Now, for the purposes of this video, it wasn't worth mentioning that. It wasn't relevant. It didn't affect the main point. My main point was where the shadow cast by the moon will hit the Earth. The fact that there's a slight variation in the angle of incoming sunlight doesn't affect this main argument. But if we want to understand why the moon casts a small shadow on the Earth, we have to take that into account. And also I'll look at why the moon doesn't take 4 days to cross this path between the Earth and the Sun. Okay, so let's look at something called the total eclipse. Okay, now this diagram here is totally non-representative in terms of scale, absolutely nowhere near it. Now, as I said, the distance from the Earth to the moon is about 30 times the diameter of the Earth. the distance from the Earth to the Sun is about 10,000 times the diameter of the Earth. And the diameter of the Sun is about 100 times the diameter of the Earth. So the diagram's absolutely nowhere near to scale, but it's to make the general point as to why the moon casts quite a small shadow on the Earth. It's because the light's not entirely parallel. But it's greatly exaggerated because on here there's quite a big angle between these two lines. In reality it's only 0.5 degrees, but because there's quite a big different distance between the Earth and the moon, that becomes significant. Now what you're seeing here is what it would be a total eclipse. And we're used to saying that the angular size of the Sun and the moon are about the same size in the sky, but they vary. Sometimes the moon is slightly bigger than the Sun, sometimes it's slightly smaller. Now in a situation like this, the moon's slightly bigger, and that's what's going to happen next month on the 21st. So on the 21st of August 2017, the moon will have a slightly bigger angular size than the Sun, so it'll completely block it out. And that's why you'll get the total eclipse for a certain radius over the surface of the Earth. If they had exactly the same size, the total eclipse would only be at one exact location on Earth at any one given time. You also get something called an annular eclipse, which is like this. This is where the moon is slightly smaller than the Sun, so therefore the shadow cast by the Sun, called the umbra, doesn't reach all the way to the Earth. So if you were at this point on Earth, what you would see is the moon in front of the Sun, but you would still see the outline of the Sun round the moon. Okay, now I didn't think that I would be able to represent this situation properly to scale on this software, but I messed around and I managed to do it actually, amazingly enough. So in this diagram here, the whole thing is to scale. So here we're only seeing the Earth, and these lines here coming from either side of the Earth, they're going straight to the Sun, to either side of the Sun. Now these two lines here, they're going to the moon, and they'll go to either side of the moon. Now this angle here is about 0.5 degrees, and these two lines here, if you extended them, they would eventually meet, and they'd be at an angle of roughly 0.5 degrees as well. So let's try and get a sense of the scale between the Earth and the moon first of all. So if I zoom out, there it is. So that's the correct scale, roughly, of the Moon-Earth system. So you can see the moon is really quite far away from the Earth. It's absolutely nothing like this, or this, or even worse, this. It's an absolute joke. And that's really significant. Now you can also see that the light from the Sun, although it's virtually parallel, because there's a big distance between the moon and the Earth, the light converges over that distance, so the moon only casts a very small shadow on the Earth, assuming a total eclipse. So let's go out even further and see how this relates to the Sun. Go to that. So I've drawn on here the path that the moon goes around the Earth. Now I've modelled it as a circle. It's not exactly a circle, but it's close, so we'll just model it as a circle. So let's go to the Sun. So there it is. So that gives you some idea of the kind of scale we're talking about. So both sides of the Sun have got lines drawn to both the moon, the moon and the Earth. So there's two lines coming from here, one going to the moon, one going to the Earth, and two lines coming from here. Now, if I zoom in on this, I'll give you a sense of how parallel or how unparalleled these two lines are. So on my video, I said the rays from the sun were parallel, which is not strictly speaking true. But if you actually show it properly, this is how unparalleled the rays from the sun actually are. These two lines are at an angle of 0.5 degrees to each other. So I don't think I was being dishonest when I said that we can assume that the light is parallel. Right. So here's the Earth and Moon system again. Now, so let's think about a couple of things. So there's two things. There's something called angular speed and there's something called translational speed. So angular speed is if I draw a line from the center of the circle to a point here and then draw another line from the center to say here, okay, there's an angle that, say a point was moving along this circle, it'll turn through an angle in a certain given amount of time. And that tells you its angular speed. It's how many degrees it'll turn through in a certain given amount of time. Now, if it's moving with a constant angular speed, it doesn't matter how big this circle is, it's got to get round it in the same amount of time. I'll get rid of that. Now, there's also translational speed, which is just the speed that the point's actually moving at along this path. Now, angular speed, we give it, oops, I'll put the pencil on. We give it the Greek letter lowercase omega. And it's 2 pi, no actually, we're doing it in degrees, sorry. It's 360 divided by the period, the amount of time it takes a point or the moon or whatever it is to get right round this circle. Now, if you're interested in a formula, the translational speed, v, can be given by pi times the radius of the circle times omega, the angular speed, divided by 180. Okay. Now you can just test this quickly. Say for a point at the equator, it would be pi times 3,960 miles, the radius of the Earth. Now, the Earth turns at 15 degrees per hour. Okay, 360 divided by 24. If you figure that out, you get 1,037 miles per hour. So, a point at the equator, as we know, is turning at 1,037 miles per hour. So that's its translational speed. Now, it's also moving at 15 degrees per hour. So that's its angular speed. Now, there's a simple relationship between angular speed and translational speed. We basically, if you double the angular speed, you double the translational speed. So if the Earth was turning at 30 degrees per hour, a point at the equator would be going at 2,074 miles an hour. I can't believe I did that on a calculator. But yeah, it'd be moving at 2,074 miles an hour. So you double the angular speed, you double the translational speed. Now the translational speed, as you can see from this formula here, is also related to the radius in a simple way. So you double the radius and you double the translational speed as well. So if it's moving in a bigger circle but with the same angular speed, it has to move faster, which makes sense. Because if it's moving with a constant angular speed, like I said, it's got to get around this whole circle in the same amount of time. But if the radius is bigger, it's got much further to go around, so it's got to be going much faster. Okay. Now, the angular speed of the moon, so let's say angular speed of the moon, is going to be 360 divided by, now, the number of hours is 655 hours. That's how long it takes the moon to go around the Earth. So it's 27.3 days times 24. So you do 360 divided by 655, and that gives you 0.55 degrees per hour. Okay, so that's the amount of degrees that the moon is turning through as it goes around the Earth in any given hour. So it's going its angular speed is much less than the angular speed of the Earth. And that's why the moon is seen to move from east to west across the surface of the Earth, the place where it's directly overhead does, which I made clear in the last video. So how much slower is it going? Well, if you do 15 divided by 0.55, so 15 divided by 0.55, 27 times slower. So that means that if the moon was moving in a circle with the same radius as the Earth, 3,960 miles, it would be going at, well, its speed would be 27 times less. So it would be going, so 1037 divided by 27, 38 miles per hour. So if the moon was moving in a radius of 3,960 miles, 3,960 miles, and it was turning at 0.55 degrees per hour, it would be moving at 38 miles per hour. So again, that's why it's kind of moving from east to west. However, the radius that the moon's moving in is much bigger. Now, the radius that the Earth, a point at the equator, is turning in is 3,960 miles. Now, the radius that the moon is turning in is 238,000 miles. Okay? So, if we do 238,000 divided by 3960, you get 60. So the radius that moon is moving in is 60 times bigger than the radius that a point at the equator is moving in. So we then multiply 38 miles per hour by 60 to get the speed that the moon's moving at. So you do 38 times 60. And that gives you about 2,300 miles per hour. Right? Now you can confirm that in other ways. You can do the circumference of this whole circle is about 1.5 million miles. So it's the radius times 2 pi, and that'll give you 1,500,000 miles. And you divide that by 655 hours, the amount of time it takes to get right round. And again, you'll get the same, you'll get 2,300 miles per hour. So whatever way you cut it, the moon is moving at 2,300 miles per hour, okay? Because although, I'll go through it again, its angular speed is about 27 times slower than the angular speed of a point at the equator, or the angular speed of the Earth, but the radius it's moving in is about 60 times bigger than the radius that a point in the equator is moving in. The circle that a point at the equator is moving in a circle with a radius that's about 60 times smaller than the radius that the moon is moving in. So you do 1,037 miles per hour divided by 27 and then multiply by 60, and it gives you 2,300 miles an hour. And again, if you can work out other ways, you'll get the same answer. So whatever way you look at it, the moon's moving at 2,300 miles per hour. And if we go in and have a closer look at the moon, And someone else said, the moon's moving in an arc, so therefore it'll follow a curved path as it moves between, as it transgresses the sun or transverses the sun between the Earth and the sun. Well, that's the amount of curvature we're talking. I think we can assume it's a straight line. And I think it's safe to assume that it's about the same as the diameter of the Earth. So take it as like 3,960 times 2, so 7,920 miles. So this distance it's coursing is about 7,920 miles. Now speed, distance over time. So time is distance over speed. So let's figure out how long it'll take to cross the sun, the light between the Earth and the sun. Distance 7,920 miles divided by the speed, which is 2,300 miles per hour. So that gives you about 3.4 hours, which is roughly how long an eclipse lasts. That's assuming that it crosses the light, taking the longest path it could take across the light. Because remember, the light is a kind of cylinder shape, so it could take different paths across it. So if it followed right across the diameter of the cylinder, that would be the longest distance, so it would take about 3.4 hours. Now the eclipse on the 21st of August is just slightly more than 3 hours. So all of this works out perfectly. There's absolutely no problem with any of it. Okay, so once again, flat earthers have just completely misrepresented the situation or misunderstood it, whatever one it is. So yeah, again, the main points is the moon crosses this light. The place where it is directly overhead is determined by the line from the moon to the centre of the Earth. The place where it casts a shadow is determined by you just draw a line straight from the moon to the Earth, following in the same direction as the sunlight. So the shadow goes right across the Earth. But the moon is really far away from the Earth. So although its angular speed is much less, its translational speed is much more, just because the radius it's moving in is huge. And you can see that the part of the moon's path right around the Earth, through which it's actually passing the sun's light that's hitting the Earth, is tiny. It's a tiny part of its whole path. So it passes through it in a very short amount of time. And that's all there is to it. So once again, flat earthers have just completely got it wrong.